All right, let's check out these two examples together. These two examples are concerned of finding the electric potential due to a point charge at a certain point, and for another one is to find the electric potential at a point due to another set of charges. So let's start with this example. The main here is that we need to use this equation because that's what the electric potential of a point charge is equal to. V is equal to KQ over R. Okay, and just to confirm that this is capital or uppercase V. Okay, all right, let's do that. So find the electric potential of a 2 nanocoulomb charge at 3 meters away. So let's say we have a 2 nanocoulomb here charge, and we need to find the potential of that charge, the electric potential of that charge at a point that is 3 meters away. Okay, so this is the point. And the way we do that is just like we use this equation. V is equal to KQ divided by R. And K is known as to be 9 times 10 to the power 9 for free space. Q is given to be 2 nanocoulombs, so 2 times 10 to minus 9. And the distance is 3, all right? So let's do some calculations. 10 to minus 9 with 10 to the power 9, they become 1 if you multiply them with each other. 9 times 2 is 18 divided by 3, so that's actually an easy calculation of 6 volts. So that's actually the potential of 2 nanocoulomb at this point, which is 3 meters away. 6 volts, all right? Look, 2 nanocoulomb is kind of like still a big charge. So at 3 meters away, you can still feel 6 volts of it. That's still big, okay? Okay, so now let's check out the second example for which we will still use the equation of the potential KQ over R. That's the equation for the potential of a point charge. Now we have a set of different point charges distributed at certain distances in a kind of like a square. So we have a charge here. I'm gonna make it red as 4 nanocoulomb, and another charge here on that other side of the square minus 3 nanocoulomb, and a third charge here, and this one is positive and it's equal to 3 nanocoulomb. Okay, we need to find the electric potential at point P. So this is our point P, so this is the point of concern for us, and we should know that the square has a side of length meter, 1 meter, okay? All right. So we have 3 charges. Each one is contributing by this much, KQ over R, all right? So the way we do that, we can actually just put them all in one equation. So we can add them all for 3 charges. We will have 3 terms. So I'm going to say K, all right, Q1 divided by R1 plus K Q2 divided by R2 plus K Q3 divided by R3. Remember, this is a scalar quantity, so we can just add all the terms together without worrying about their direction. Okay? Okay. So let's call this number 1. Let's call this number 2, and let's call this number 3. Okay? Number 1, so K is a common number for all of these, so we can take it out, and it's 9 times 10 to the power 9, just to make things easier for us. So I'm going to say here Q1 over R1 plus Q2 over R2 plus Q3 over R3. All right, let's start again with number 1, so that this term comes down. Q1 is equal to 4 nanocoulomb, so I'm going to say 4 times 10 to minus 9, right, divided by the distance, which is 0.5, plus Q2, which is minus 3 times 10 to minus 9, divided by this distance. I'm going to call it R2. And R2, using Pythagorean theorem, is equal to this square plus this square. So 0.5 square plus 0.5 square. And with some calculation, I can find this is equal to 0.707 meters. So I'm going to put here 0.707 plus Q3, which is 3 times 10 to minus 9 divided by the same distance as this one, which is 0.5. Now, to make calculations easy for you, we just have to look at what cancels out. All of this you can take out 10 to minus 9 with this one, because if you multiply the terms, you're going to end up with 1, all of that. And now what's left is just a quick calculation, and if you do that, you are going to get the voltage equal 87.9 volts. So that's the contribution of all of these charges as a potential on this point, 87.9 volts. And that's it for this problem. Thank you.